Lesson 38, balancing equations. So we will be able to balance chemical equations. Now this is a skill that you should have learned in year 9, but usually in year 9 we pass over balancing equations very quickly. It's not usually a focus. So that means that in year 10 we need to go back over it and go over it in a little bit more detail. Before we do that, let's talk about what we talked about last time. Last time we talked about, well, how can you tell a chemical reaction's occurred? We talked about these types of definitions. An atom, a molecule, is 2 or more atoms joined together. A compound is, again, 2 or more atoms joined together, but they have to be different. And an element can be 1 atom, or it can be more than 1 atom, but they have to be the same type. I actually found the picture that I was looking for. So this is the picture that I've had before. Or as you can see, all 3 of these are molecules. Sometimes the molecules have the same thing, sometimes they have different things, sometimes they're really big. But yeah, so these 2 are molecules and they're compounds. A compound means you have to have different things. And a mixture, this is a bonus one. It just means you've got different things, but some molecules one thing, and some molecules of a different thing, all mixed together. That might be something like carbonated water, where you've got a mixture of water and carbon dioxide. Or it could be even air. Air is a mixture of nitrogen and oxygen. So yeah, we talked about chemical and physical change. Physical change is all about breaking something, is all about just changing something. You can either change the shape or you can change the state. So like dissolving a solid in a liquid. The theory here is that you could put all these blocks of wood together to get back to the big block of wood on the left if you had enough time eventually. Changing state is the same sort of thing. If you dissolve a piece of metal, a piece of salt in water, if you remove the water, you would get your salt back. So you can go backwards. That's one of the ways you can tell physical change, is that you can go backwards. With a chemical change, that's it. You can't unburn a piece of wood. You can't unrust a piece of metal. You can't
Wait, what?
What?
Wait, what did you say before? You said you can't unrust metal?
Yeah, you can't unrust metal.
Wait, so how come there's like videos and stuff about like people pouring coke and shit on the like metal stuff?
So what you can do
and it's like gone.
So what you can do is you can remove the rust with a chemical. That's something that you can do. You can remove rust. And there is a way that you can like change stuff with, but you can't. Ultimately, one thing you just can't. You can't take rust metal and go back to iron. You just can't go straight backwards.
So it's still there, but it's like not there, you know?
Yeah, I know what you mean.
Okay.
Right, starting material, final material. We have names for these. We call these reactants and products. And then we talked about these are the 7 signs that something's changed in a chemical reaction. You don't necessarily need to be able to memorize each of these, but you need to be able to identify them. You need to, if someone says, oh, I added this chemical to this chemical, and you know, and nothing changed, but it started to smell like bananas. Well, then you've got a chemical change because you've made something new. You've got a new smell. You might, when you did that reaction, you may have gotten also a temperature change. So the system may have heated up. So keep those in mind. You don't need to memorize them all, but you do need to know when you see one of these things that means a chemical reaction's happened. We talked about these laws, and ultimately you just can't make new atoms. That's how chemical reactions work. We're actually going to look at that in a second. And then we finished up with states. So we've got 4 states we usually use: solids, liquids, and gases, and aqueous, which means it's dissolved in water. Okay, a lot of our reactions are reactions from things that are dissolved in water, so aqueous is probably the one that you use the most. Then we talked briefly about explosions. Explosions is when you make a lot of gas really quickly. I showed you 3 explosions. Not all of these are bad explosions. Of course, burning gas can help us cook food and things. So just, you know, an airbag save our lives. But of course, explosions can also be using gunpowder and stuff like that. So they're not always a good thing. So today we're going to talk about balancing equations. We're going to start off with some simple equations and some simple rules, and then we're going to build up to more complex ones. So let's start off with how to balance an equation. We're going to start off with, before we move on, we're going to talk about one more thing with regards to explosions. We're going to do the reacting sodium with water. The reason we're going to do this one is because it's actually the main question that they talk about in the sodium metal in the style lesson. They talk about what happens when sodium reacts with water. What happens when sodium metal reacts with water? Would like you to copy this down, by the way. It makes salt, and also something. It also makes hydrogen. So let me show you how it does that. So what you do is you take sodium metal, Na, because that's the symbol for sodium. You take some water, H2O. And what you do is you end up getting NaOH plus H2. Now, technically, guys, just for the record, this isn't balanced. I need to fix this up to make sure this is balanced. To do that, I need to put this. I need to go 2, 2, and 2. Well, I'm about to show you guys how to balance these, but at the moment, I just want you to quickly see how these would look. Now, the first thing that we can tell is sodium explodes in water is because it makes, as I said, the rule one is it makes a gas, and that gas is going to be expanded out. That's why it'll bubble, and if you put a large enough piece of sodium in there in water, it will make a lot of gas bubbles and that will be a little bit of an explosion, a little bit of a pop will happen. I don't need to remind you guys too much about what happens when sodium reacts with water, because you guys have all seen what happens when sodium reacts.
Wasn't that the explosion thing?
Yeah.
Yeah, that thing.
So what I was trying to do was what was essentially a secondary explosion. You see, the thing about sodium with water, and this is actually, they talk about this in the actual topic, in the actual thing, is that you'll notice that you make a lot of hydrogen gas. Okay. Now, the thing about hydrogen gas is that hydrogen gas is flammable. If you take hydrogen gas and you react it with oxygen, you can actually create H2O gas. That's another explosion that you can make. And that releases a lot of gas at a very, very high temperature. So that's how you can make another explosion. And that's actually what, and I've talked to you guys briefly about this already, that's actually how I ended up making that big mistake, is because I actually wanted you guys to see this happen. I wanted you guys to see the hydrogen igniting. In this picture, that's what these flames are. That's the hydrogen igniting. Now, the first initial explosion is not the hydrogen igniting. It's the first initial explosion is the gas, the hydrogen being made. Only afterwards can you ignite the hydrogen, which makes a secondary explosion, which is really hot water. The problem, of course, without me going into too much detail, I want you to copy this down as well, by the way, is that, yeah, the reaction emitted too much energy, which broke the glass. The other problem as well that I, didn't want to publicize too much is that we ended up making a lot of really hot water vapor, which had sodium hydroxide. I'm not sure if you guys remember, but that's actually why the room like felt like a bit weird and tasted a bit weird, is because we made a lot of like basic salt in the air, and yeah, it wasn't great. But that's the explosion, and that's how that works. And the reason I'm doing this is because in the style activity, they really explore why it is. The main thing I want you to get is that there are two reactions going on. This is the first reaction, and this is a second reaction. That's why it's sometimes really dangerous to make hydrogen, because if you react something and makes hydrogen, you can actually get two explosions for the price of one. Yeah. Are there any questions on this, or any queries? Because I'm about to jump on.
No,
You good? All right.
just keep it going.
So those are the two reactions. If there's anyone that needs me to slow down, please let me know. You can also private message me in chat. I think you can do that. So then you can be like, hey, sir, can you slow down a bit? And only I will be able to see it. But yeah, hopefully that wasn't someone emailing me, because I won't be able to see that one. So I'm going to show you guys now. We're going to build up to chemical reactions. The first step is to understanding chemical reaction is an ability to count atoms. And this is exactly what we just did in that previous example. The question here is, how many oxygen atoms are present in each of the following compounds? For this first one, and I want you guys to write this down, for this first one, CuO. How many oxygen atoms do you guys think that are present? You can answer in chat, or you can answer out loud, up to you.
One?
One. There is one oxygen atom.
Yeah.
Why?
Oh, what does the S mean?
Solid.
Oh. Okay.
So this is cupric oxide or copper oxide. There's one oxygen atom because there's no number in front of it, there is no number behind it, there is no little curly number, so there's just one oxygen atom. On the right, actually, here is a picture of copper oxide. This is what copper oxide looks like. Copper oxide is actually what happens when copper gets oxidated over time. That is why the Statue of Liberty is this greeny blue color. It's also why a lot of the roofs a lot of the old roofs in Florence and Rome in Italy are also this color. What happens is that over time, copper turns into copper oxide. So actually kind of cool to think about. When the Statue of Liberty was first, built, it would have actually been this big brown colored shiny sculpture, and now it's actually this bluey kind of color. Anyway, let's move on. H2SO4. Now, how many oxygen atoms do we think are present in this one?
4?
Yeah. What you do for this is that you would look at this. Oh, there's a 4 right there. So that means that there's going to be 4 oxygen atoms. Okay, so CuSO4, there are 2 hydrogen atoms and there is only 1 sulfur. This is sulfuric acid, this is battery acid. We've had sulfuric acid for millennia, so it's kind of cool, for thousands of years. Last one here is aluminium nitrate. Okay, can someone tell me how many oxygen atoms do you guys think there are in this?
9. 9 life.
There are 9. Now the reason why there are 9 is because you would say, oh, there is 3. But the trick here is that there are 3, but then there are 3 copies of that 3. So 3 times 3 is 9 oxygen atoms. There's also 3 nitrogen atoms. It's the same, it's exactly the same as the previous one that I did in today's The attendance question, remember NO3 just means that there are 3 copies of NO3. So if you count 3, 6, 9, that's how you get your 9 oxygen atoms. We never expand things out like this in real science. I'm just showing you guys this so maybe it gives you an idea of, oh yeah, it's kind of like maths. It's kind of like expanding in maths, except it's not. It's in science. It's like, yeah, it's actually similar. But yeah, you just got to remember that means there's 3 copies. Are there any questions on this? Because I'm about to move on.
No.
Nah.
No? Okay, cool. So let's take this to the next level then. I want to know how many hydrogen atoms are there on each side of the reaction. Can you guys tell me how many hydrogen atoms are there on this side of the reaction?
6.
6. Yeah, there are 6
Yeah.
hydrogen atoms.
Uh-huh.
And how many are there on this side of the reaction?
2.
2. Here's the question for you. Do you think that this reaction is balanced?
No.
No.
No. Now, I'm not going to balance this question yet. I'm actually going to balance this equation in period 6. But this is not balanced. Can you guys tell me why is this not balanced, do you think?
Because the reactant side has 4 more than the product side.
Yeah. So,
Yeah.
you know, we've got extra, it's not balanced because we've got extra hydrogen on one side. Now, if I was going to tell you what we need to do to start to balance this, what you would do is you would say, well, I'm going to add more hydrogen to the right-hand side. And there are some techniques that I'm going to show you in a second in how you might do that. But yeah, I'm going to keep this up for just a little bit longer, maybe another 30 seconds, just because I want people to copy this down. But yeah, just understanding that this is not balanced is really important. You could also find out it's not balanced by counting the oxygens. There are 2 oxygens on the left, but there are 5 oxygens on the right. So again, not balanced at all. If you can't see why there are 5 oxygens on the right, maybe have another look. Remember, it's CO2. There are 2 oxygens in carbon dioxide, but there are 2 copies of that carbon dioxide. Okay, I'm going to move on. Are we good?
Yeah.
No, hold on.
Right. It's fine.
I'm close.
That's all right. Take your time. So let's see. We've
That's
got oxygens. We've got 1 here. We've got 2 times 2 because there are.
I hated this part last year.
Well,
This part was so hard when I did it last year.
I'm done. You can go.
Okay. Well, hopefully, you know, maybe with the best teacher in the school, you have a bit more luck. All right.
Yeah, you're a little funny.
What are some of the rules that we need to do when we balance equations? Now, these are some rules. Well, the first 2 are rules. The second 2 are more suggestions. The first rule is you've got to make sure the reaction obeys the conservation of mass rule. That means that you can't just have more hydrogen on one side and less hydrogen on the other side. They have to be balanced. You have to have the same amount of hydrogen on both sides of the equation. Okay? The second one is you do not change subscripts. If you find out, oh no, there's not enough oxygens on the right-hand side, I'm just going to change this from NO3 to NO4. You can't do that. That's not allowed. Okay? The reason that's not allowed is by changing that to NO4, you're actually changing the chemical. You're actually changing the molecule. But if I go, oh, I'll go to NO3, you're not changing the molecule. You're just adding more copies of that molecule. So that's why you can't change the subscript. You can't mess around with them. It's always suggested that you balance the metals first because they're the easiest ones to balance. And the ratio of the coefficients, which means the numbers at the front, should be as small as possible. So if you can make it so that there are 10 CO2 plus 4 H2O, whatever it is, you should be able to say, hey, I can simplify that to 5 CO2 plus 2 H2O, because, you know, these numbers, I've just divided everything by 2, and that's now a bit simpler. It's the simplest form. I really should have one more rule, which is, you know, it's not really a rule, it's more of a suggestion, but you want to add new atoms to balance. That's how we balance things. We don't try and say, oh man, there are too many hydrogens on the left, let's remove some of those hydrogens. That's not how you balance things. If there are too many hydrogens on the left, you can balance things by adding more hydrogens to the right. Now, these rules are a bit random. They're a bit out there, and I don't like teaching you guys how to balance equations just based off rules. I much prefer showing you guys actual examples. So what we're going to do is we're going to do an actual example in a second. We're going to do I'm going to try and do 3 examples, but looking at the time, I've got about 10 minutes left, a little bit more, about 11, 12, but I'm not sure if we'll get through all of the examples, but we're going to give it a try to at least get through as many as we can. And I'm going to keep going through these examples because, as you guys have said, and this is true, students find balancing equations sometimes one of the hardest things to do in chemistry and in science. And I want to try and get you guys familiar with the kind of skills that you need to know to be able to do this. And hopefully by the end of it, you know, you guys can handle even the hardest questions. I might even give you the year, maybe period 6, I could give you the permanganate question. Permanganate is the hardest, is a year 11, as a year 12 chemistry balancing question. And it's actually really difficult to do, but I reckon maybe you guys can handle it if I teach you guys well enough. But I'll get to that in a sec. I'm going to change the slide. Are we all cool if I change the slide yet?
Yes. Yes.
Yes? Okay.
Yeah.
Let's power on then. So we're going to do our very first balancing act. We're going to do a couple. We've got 2 easy ones and 1 harder one. We're going to do this one first. Now, I haven't put states on this. It doesn't matter too much. Can I get you to write down this formula here? AgI plus Na2S goes to Ag2S plus NaI.
Wait, is that an I or L?
It's an I.
Oh, okay. Cool.
Now, from term 1, you guys, in theory, and I know this is a theory, should be able to tell me what these are. This Ag is sodium, I is iodine. So because it's iodine, and that's our negative ion, we refer to this as silver iodide. We replace the iodine with an iodide. And that means that, and this one here is sodium sulfide. Because the S is at the end, you add IDE to it. That goes to make silver sulfide. Hold on. Plus sodium, sodium iodide. That's the worded version of this equation, but let's dig in deep with this. Now, how do you balance an equation? How would I balance this equation? What I would do is I would start with the metals, okay? And what I'm going to do is I'm going to, actually, you know what I'm going to do? I'm going to list every single, I'm going to list, the first I'm going to change to blue. I'm going to list every atom. We've got silver, we've got iodine, we've got sodium, and then we've got sulfur. Then what I would do is I count how many of each are there. How many silver Ag atoms are there on the left-hand side of this equation? Someone?
One.
One.
One. Good. How many are there on the right?
Two.
Two.
Two. Let's do iodine. How many iodines on the left?
One.
One.
And on the right?
One.
One.
Sodium?
Two.
Two.
Two. And on the right?
One.
One.
And then sulfur.
One.
One.
And on the right?
One.
None.
There's one.
Oh, there's one. Never mind. I didn't see that.
If I was to look at this, I'd say, oh, we've got a problem here, right? Got one silver atom on the left, but two on the right, okay? So I'm going to circle this. I'm going to do a little red line here. That's not balanced. And the sodium is also not balanced. I've got two on the right, but only one on the left. Okay, so how do I balance this? Well, how I would balance this is like this. I'm going to put a 2 at the front of this equation. Why? Because then I can change this 1 into a 2, and now the silver is balanced. But if I put a 2 there, what have I also changed?
Iodide or whatever it's called.
Yeah, how many iodines have I got now?
Two.
2. I've got 2 on the left. Great. You know, shit. I balanced out the iodine. I balanced out the silver, but now I've made the iodine unbalanced. Okay, so then what I would do is I'd say, well, maybe now I'll move on to the sodium. I've got 2 sodiums on the left, and I've only got 1 on the right. So I'm going to make sure I've got a balance of sodium. So to balance out sodium, I'm going to put a 2 here. If I put a 2 there, then that changes this one to a 2. Yeah? But what does that also change?
Iodine.
And how many iodine have I got on the right now?
Two.
1.
Oh.
2 times 1 is 2. Now, but that's fixed up my iodine problem. So let's
Mr.
check.
Bear, can you explain it again?
Okay, so what I've done is I've put a 2 here in front of the sodium iodine. Why? Because I've got 2 sodiums on the left. I want to make sure that there are also 2 on the right. So if I put a 2 here, I've got now 2 sodiums. But here's the problem. Now that I've got 2 sodiums though, I also have 2 iodines. So I have to change this 1 to a 2. But that's actually a good thing, because now there are 2 silvers on the left and the right. There are 2 iodines on the left and the right. There are 2 sodiums on the left and the right. And there is 1 sulfur on the left and the right. This is now a balanced equation.
Congratulations.
Yay! So that's how you balance an equation. Now you could actually have done this a different way or similar way, but you could have said, oh man, if you had started and said, oh, I want to balance the sodiums first, you would have still got to the same point. Because if you balanced the sodiums first, you would have said, now I've got too many iodines on the right. I have to make sure I balance the iodines and add 2 to the left, and you would have balanced it out. But this is a simple example. We're going to do one more example before the bell goes. And then what we'll do is period 6, we'll go through a few more examples just to build up some more practice. And then I'm going to let you guys go on the style. because the style's got a lot more practice for you guys to do.
Oh my days.
And
Right.
what the other science teachers have done is they've uploaded a worksheet to the style activity. So I actually expect this style activity to take you a while to do. So I'm not going to make it due in a week's time. We're going to make it due a lot later, but we'll talk about that later on. One more example for today, for this lesson, is going to be, this one here. KHCl goes to KCl plus H2. This is actually looks like it's a bit of a reaction. It's going to produce hydrogen gas. So let's see how this would work. The very first thing we're going to do is we're going.
K potassium.
Yep, K is potassium.
Mm-hmm.
I'm going to find out how many Ks, how many H's, how many Cls are on both sides of this equation. Okay, so let's do the first one. How many Ks on the left?
1.
1.
How many Ks on the right?
1.
1.
How many H's on the left?
1.
Wait, 1.
How many H's on the right?
2.
2. How many Cl's on the left?
1.
And how many Cl's on the right?
1.
1.
So if I look at this, 1 goes to 1. So hold on, let me just change the color. 1 goes to 1. 1 goes to 1. 1 goes to 2. Okay.
Oh, you just got to put a 2 in front of the HCl and call it a day.
Well, let's check that.
It changes CL.
I put a 2 at the front of this HCl. Yeah, sure, done, cool. That becomes a 2. But now I've got too many CLs. I've now got 2 CLs.
So oh wait, never mind.
Oh, okay. I didn't think of okay.
So you can't just call it a day, but we're on the right track now. So now which of these is unbalanced?
CL.
CL is unbalanced. How can I balance out the CLs?
You put a 2 in front of the K. CL.
Yeah. So let's do this in a different color. Let's go with red. Let's put a 2 here. That's going to now change. There's now 2 CLs. Perfect.
Uh-oh.
But what else?
The K.
But
The K is affected.
The K gets affected. All right.
And put a 2 in front of the K.
But now, but I just got to increase the amount of K's here. So if I go to, I don't know, what color am I going to go? Let's go brown. If I go a 2 here, then that changes this 1 to 2. But there's nothing else in this molecule, so I can just leave it. Now,
just leave it.
Now let's check. So now, let's see. I have 2 on the right, 2 on the left, tick. 2 on the left, 2 on the right, tick. 2 on the left, 2 on the right, tick. This is now balanced.
Let's do the third one. I bet I can do the third one easy.
Do you reckon we can do the third? No, we can't do the third one.
Yeah.
It's 10:35. We're about to run out of time.
I don't care. If everyone leaves, I'll stay back. I'll just do it. I want to do it.
Listen, I'm going to do the third one now, then, but I will redo the third one, period 6, okay? We're on a roll. I'm going to redo it at period 6. When the bell goes, you guys are more than welcome to leave, but I'm going to do the third one just because we're on a bit of a roll. But you can see why. This is a challenge.
Hold on.
That looks a little too easy for me.
So we've got a lot of different atoms here. We've got
H or whatever. I don't know.
We've got H. You've got N.
You got NO.
We've got O.
Yeah.
CA.
And then CA.
CA. And
you got a C.
CO. Yeah. Wait, and then you got oxygen, is it not?
Yeah, I've already
No,
done
but we already wrote oxygen.
Ah, okay.
That's the bell. Do you sure you want to do this now, or do you want to do it period 6?
Yeah, I just want to do it now. I want to get this out of the way.
All right, we'll do it now. So there is 1 hydrogen on the left. How many hydrogens on the right?
2.
2. Because there's 2 in the water. How many nitrogens on the left?
1.
3.
1. Now that
Oh,
3
okay, no mind.
is only attached to the thing. How many nitrogens on the right?
2.
2.
2. Because 1 times 2 makes 2. How many oxygen? How many oxygens on the left?
6.
There is not 3.
I said 6.
There are 6. Yeah. There are 3 here and 3 here. That makes 6. What about on the right? How many oxygens are there on the right?
There are 8.
No,
9. There's
9.
9.
9. It's
There are
9.
9.
Yeah. 9. Yeah.
How many calciums are there on the left?
1.
And how many calciums are there on the right?
1.
And how many carbons are there on the left?
Yeah, whatever she said.
1.
1. There's 1 carbon here.
Mm-hmm.
And how many carbons are there on the right?
1.
Okay.
Yeah, there is just 1. Just here.
Uh-huh.
So now we've got all of the atoms identified. Let's see which ones of them are balanced, which ones are not balanced. So hydrogen is not balanced. Nitrogen is not balanced. Oxygen is not balanced. Calcium is balanced and carbon is balanced. So they're okay at the moment. So which one are we going to do first? I would strongly suggest doing nitrogen first. I always leave hydrogen and oxygen for last.
Why?
Because notice how there are lots of places where there are oxygen. There's oxygen in carbon dioxide, there's oxygen in water, there's oxygen in the nitrate, there's oxygen everywhere. So oxygen I save to the end. And for the same reason, I save hydrogen to the end. Usually there's hydrogen just hiding out everywhere. So I usually wait for the very end for those last 2. And you'll see, so that means that the first one I'm going to deal with is going to be dealing with the nitrogen. How can I balance?
You just got to put a 2.
2 where?
In the first reactive thing.
All right.
No,
so
I meant like between N and O.
Wait, can you do that?
Can you even do that? Yeah, can you do that?
Like
Can I
H
do,
and then
can I do that?
Oh,
Shit. Never mind.
never mind.
So if I change that to a 2, that's going to change this one here to a 2. But what else is it going to change?
Hydrogen and oxygen.
So now I've got 2 hydrogens, and how many oxygens have I got?
Oh wait, crap, because
8.
2 times 3 is
6.
6.
plus 3.
Wait.
9. Wait, what? I'm so confused.
Wait, so 2 times 3 in the first reactant is 6 plus 3.
Yeah, 6. Plus 3 is 9.
So now that's balanced, and then I go.
That's balanced.
That's done. So if
The whole thing's balanced.
Check now. 2, 2,
Hey,
that's
Mom.
balanced. 2, 2, that's balanced. 9, 9, that's balanced. 1, 1, that's balanced. 1, 1, that's balanced. Everything's balanced.
Oh my days, is that it?
Let's go, baby. Let's
I
go.
was actually thought that this was going to be a lot harder.
I thought
That's
it was
why I
gonna
was
be
like, oh my God, guys, we're going to be here for a while. But then I thought, then I'm like, oh, look, that's it. That's all we have to do.
Right, let's go, Mr. Greer.
Yeah.
See?
Let's go, baby.
I will see you guys period 6. We're going to work on a couple more examples that are a little bit more challenging, and then I'm going to give you guys a chance to style.